Hi everyone, Architecture and Operating Systems. We are in week 14 and in this week I'm going to explain more about IAS computer which I introduced in the previous week. So what we did last week was talking about the computer architecture and computer organization. Computer architectures talks about those attributes that have a direct impact on the logical execution of the program. And computer architecture refers to operational units and their interconnection that realize the architectural operation. So as you see here, for example, these two cars have got the same architecture, the logical design of them. But in terms of the interconnection and the components, they are different. So the computer architecture, it talks about the logical execution. Organization talks about how the different parts are interconnected. Then we discuss about the computer functions, the main four functions, and 3 levels of computer structure. And also, we talked about Van Neumann architecture or IAS machine. The computer functions that we discussed was data processing, data storage, data movement, and data control. And we discussed that for data movement, data processing, and data storage, we need to have these control mechanism at the heart of this orchestra. Also, we discussed the computer structure in 3 layers. In the top layers, we've got input-output device like printer, keyboard, screen. We've got main memory, CPU, and we've got the interconnection tool system between them, which we call them buses, system bus, that send and receive the data between these 3 parts. And also we looked at inside the CPU, and I showed you that we've got ALU, which is called arithmetic logic unit, something that we discussed in first teaching block, how to create a circuit, how computer works based on binary numbers. We've got registers that I'm going to explain today. We've got control unit that controls all the operations, sending the signals, and also we've got internal buses which send and receive the data between these 3 elements inside the CPU. So we discussed about the stored program concept in Van Neumann architecture or IAS machine. In the ENIAC, the first machine that was developed in 1946, they used wired and vacuum tubes to program. It means that manually they put these logical gates, let's say, together. They create a circuit that we did in the first teaching block, for example, for adding 2 numbers. They did that manually, and then they loaded it by the data and got the results. But it wasn't quick enough. It wasn't efficient. And Van Neumann in IAS machine proposed something new, that they can store both data and instruction, which means the program, on the machine. The task of entering and altering programs for ENIAC was extremely tedious. But suppose a program could be represented in a form suitable for storing in memory alongside the data. Then a computer could get the instructions by reading them from the memory, and a program could be set or altered by setting the values of a portion of a memory. So that was the main difference between IAS machine and the one developed before. So they could store both program and data on the machine. This is the proposal or architecture of IAS machine, that it's got 4 parts: main memory, input-output devices, ALU, arithmetic logic unit, ALU, and control unit. This is called CPU. And in this machine, this architecture, we store both program and data on the memory. We do the operations in ALU. We know how that happens. We know actually logical circuit, we know optimization to actually make a very efficient operation. And it's this part, program control unit, controls how that works and the rest. And also we know that we can get the data from input devices like keyboard and output like printer, for example. So this is the architecture of the IAS machine that even today we are using the same architecture but with different organization and different components. In this machine, IAS, we store, I said that it's a stored program concept. It means that we store both data and instruction on the machine, on the memory. So how is the memory? In the IAS machine, they had 1,000 locations in the memory. 1,000 locations, both for data, as you see, 39 bits for the number, 1 bit for the sign. We know that very well from the first teaching block. And then we've got words, or 40 bits for instructions. In each instruction, in this machine, they had one left action instruction and right instruction. In each part, in each instruction, we've got opcode and address. What it means, for example, we want to say, add 2 numbers. For example, you write a program x equal to y equal 5, z equal x plus 5. X equal to will go and sit here in one of the words. It's addressable. It's got a location. For example, in location 1, you store x. In location 2, or 5, 10, whatever, you store the second number, which is 5. So next one, you've got to add the numbers. What number? For example, number 1 with number 5. I mean, the location 1, location 5. So we've got to give the address. This is the program that we write. We've got to have address, and also we've got to tell the machine that you've got to add them. We use opcode 8 bits to show that, to say that, okay, now we want you to add these 2 numbers. So the opcode that I'll show you the list of the IAS opcodes, 21 is actually opcodes, that what happens. So the computer gets these opcodes, interpret that, and then execute this. So we've got 2 types of words, number words and instruction word in IAS machine. So here, Van Neumann architecture, I said that we send, receive data between them, but we need temporary storage between each of these, between every 2 of these machines. Even between these 2, we've got some direct links, but they should have capability of storing bytes or storing bits, let's say. So what's that called? They call register. So registers are the temporary storage between here inside the CPU that they can store the data temporarily between different components of this architecture. We've got several types of storage registers nowadays. Very quick memories they are. But here I just tell you the most important one that are used for IAS machine. So this is our IAS architecture. We've got input output. This is the main memory. This is the ALU. And this is our program control unit here. As you see here, guys, they are all registered. PC, MAR, IR, IBR, MBR, all of them are registered. They are temporary writable memories. The first one is memory buffer register. As you see, memory buffer register send and receive the data to the input output equipment. It send and receive data from main memory. There is a link between them. You can write on the memory from here and you can read from here. It's a buffer. And also it send, when it gets an instruction, it send the instruction to the CPU. And when it gets it, when there is a data here, it sends it to the ALU because it's a stored program concept machine. So we've got both data and instruction. So what happens? Send both data and instruction. data here, instruction to the CPU. The first one is memory, the second one is memory address register. Imagine that we read the data, which is an instruction, goes to the MBR. In MBR, it realized that that's an instruction. So it sent it to the CPU to understand what it is. As I showed you here, each instruction has got address and opcode. So this MAR specifies the address inside the memory. The next one is IR. It's actually decode the opcode. So we break the instruction here into address and opcode. Address goes and specifies the address that we want inside the memory. Opcodes understand what it is and send it to the control circuit to send a signal to the ALU. I will explain that in more details. Instruction buffer register is here. Usually in IAS machine, they use the left instruction. But if they got a right instruction here, the right instruction will go to the IBR, and then the opcode will go to the IR, and the address will go to MAR. So instruction buffer register, it's a buffer for instruction for the right instructions on the 40 bits word. And program counter specifies the next instruction that should be fetched or executed, that should be read or should be done. So it shows the next line of the program that should be done. Accumulator and multiple questions here, when actually an operation is undertaken in ALU, in a circuit, so the 14 most significant bits will go inside the AC, and the 40 less significant bits goes to MQ. Generally speaking, the result will go and save here, and then they can be stored on the memory, or they can go to present as an output. So these are the most important registers that we have. How computers use them? In two cycles, fetch cycle and execute cycle. In the fetch cycle or reading cycle, we read the instruction. It means that we start, because the computer works line by line in the memory, it starts reading from, for example, a specific place like 250, start reading and going down line by line in the sequential fashion. So first of all, we read in the reading cycle, we call it fetch cycle. We read it, we read the instruction, go to MBR, then send it to the MAR and IR. The address will go to MAR, the opcode will sit in IR. This is called reading cycle or fetch cycle. In execute cycle, we understand what opcode is, and then we start doing that operation, adding, subtracting, whatever. So when the IR gets the opcode, it goes and to the interpreter, and it's been interpreted and send the right signal. For example, the opcode is for adding two numbers. Actually goes to the control circuit in interpreter here, and we said, okay, now send a signal to the ALU. You've got to add these two numbers that are coming. You've got to subtract it. It depends on the opcode. What numbers? MAR will tell us where to go and find that. So fetch cycle talks about reading, execute is about executing. Computer works in fetch execute cycle, and all the operations happen here. Opcodes that I told you, look, 21 opcodes exist in a IAS machine. For example, adding two numbers, 0000101, it's about adding. Add MX to AC, and this is the description, and this is the symbol for that. Subtract 00110. Multiplication 1011. As you see, we have 21 opcodes here that IAS machine used to do the operations. So this is IAS machine. We've got three main concepts which are very important. First of all, Single read-write memory. We can both read and write data and instruction on the memory. It's a stored program concept. The memory is addressable. It's very important because we should know where to store the data, where they read the instruction from. And execution occurs in a sequential fashion from one instruction to the other one. So when you write a program, for example, your program starts from the location 125, 126, 127. So it goes line by line in the memory and goes down in a sequential fashion, unless explicitly modified. For example, an interrupt happens. We'll discuss that later. So these are the most important or key concepts in the IAS machine or Van Neumann architecture. Two things. First of all, programming in hardware. In ENIAC, what happened that I said that they used hardware, they used hardware to actually create arithmetic logic unit or function. For example, we did that using logic leap, create a circuit. So we used programming in hardware. So you create your circuit manually by hand, then load the data and you get the result. So what we did in the first teaching block was all about programming in hardware, because manually we created a circuit. This is not happen, this is not efficient. In the stored program concept, I'll tell you, but look, this is a circuit, for example, that students designed for a burglar alarm system. So using logically, put all these gates together to be able to create a burglar alarm system. The other one, the picture is an actual hardware programming hardware or hardware actually tool that they use for programming. But programming in software is different. What happens? I said that each instruction has got an opcode. The opcode, it goes to the control circuit or instruction interpreter. So it goes and read it from the table. Okay, this opcode is for adding. It's interpreted here, and then send the control signal to the general purpose arithmetic and logic unit. Imagine that I want to add two numbers. I've got a single adder subtractor circuit. When you want to add, so you've got a specific opcode for adding. So the instruction interpreter understand that's the adding. Send the signal to the general purpose adder subtractor that we have, that okay, this is adder, this is adding operation. You need to turn the external switch off. So that happens. And then you get the data from the memory, because you can both store the data and instruction on the memory from the memory, and then load it with the data, you get the results. If you want to subtract two numbers, the opcode is about subtraction. So you, the instruction interpreter understand that says subtraction, send the signal to the general purpose adder subtractor that we have, and says, okay, now based on this, this is the signal, and you need to turn the external switch on, the one that we have. I'll show you in adder subtractor. When you turn that external switch on, it means that you have subtraction. So then you load the data and you get the result. So inside the ALU, what happens is that we've got a general purpose arithmetic and logic functions, and based on the signals that we get from the instruction interpreter, we actually form a new circuit, the one that we want to use inside the machine. This is called programming in software. The opcode comes interpreted, send the signal to frame the ALU to create the right circuit for us, and then load the data and get the results. This is called programming in software. That's what we are doing on our machines. So where does it go? It sits here. Interpreter and all of them will sit here. The instruction and the data sits on the memory, so we get them from here. Interpret that, send the signal to here, and then, oops, and then give the result back to input-output device. So this is how computer works in IAS architecture. Top level view of that, we've got the CPU and sorry, we've got the CPU with all the write registers that we have, and also we've got execution unit or ALU that we discussed. We've got input-output modules. We've got buffers here. We've got places here, ports, for example. We've got different ports for printer, for monitor, for whatever. We've got main memory, which is addressable, as you see, from 0 till the last one. For IAS, we've got 1000 location. We've stored both instruction and data. We know that instructions can be interpreted by the interpreter and send the signal to the execution unit. Between these three units, what we have is system bus that we'll discuss it later. Inside the CPU, we've got internal bus that again we'll discuss it. So this is the top level view of the computer components in IAS machine. Chapter 2 and 3, if you want to read that, it's available on the library. You can borrow that. Next week, instruction, fetch and execute. I'll go in more details of how exactly computer works. Thank you much, guys.